My name is Ben Nieswender. I'm the Director of Learning here at ArduSat, and I am very excited to introduce Chris Hoffman. He's our Community and Learning Manager. He's got a lot of years' experience in education technology, and he's got some really great things to share with you today. So here he is, my good friend, Chris Hoffman.
Oh, thank you. Such a warm introduction, and deservedly so. So welcome everybody to the webinar. Thanks for taking the time today to hang out with us and learn a little bit about Arduinos and what we do. Like Ben said, I am the Learning and Community and Learning Manager. Boy, so difficult these days. But moving the microphone just a little bit. What we're going to be talking about today is Arduinos in the classroom. What I want to get to you is a little bit of background history on the Arduino if you don't have one, and some practical advice on how to move forward with your integration of Arduinos into your classroom. So I'm Chris Hoffman. You can see over here on your left-hand side that this is a CubeSat. This is one of the products that ArduSat offers. It is powered by an Arduino. That's that green board in the middle, and it has a whole bunch of sensors at the top. What we do is we try to use these sensors to teach kids about STEM careers and STEM education by learning how to talk to these sensors, which are the exact same types of sensors that are sent into space. Our partner company, Spire, should have about 100 of these up in the next couple of years. And so we're really excited to get all of that learning and education to the students. But talking to a satellite is a progression. You start from having never talked to a satellite all the way up to talking to one. So that's how our progression on our learning stuff works. But when I go to conferences or when I am talking to somebody who wants to get involved with Arduinos, one of the questions I always get is, how long will I need to learn this stuff? And unfortunately, it's not a silver bullet answer. The answer is it depends. But the thing I want to instill into people is that you can do it. Don't be afraid of all the big scary things that are coming along with this, with like electronics, code, all the different bits that come with it. It can look really intimidating, but if you follow the steps that we're going to sort of go through here in this webinar, I'm sure you're going to be off and running with your Arduinos in your classroom in no time. So if you've never heard of an Arduino before, this is one of your very first introductions into it. This is on the left-hand side, you have one of the very first Arduinos that was ever built. This, the Arduino itself is what's called a platform. So it's not it's the combination of all the electronics that are on that board. And it's also what they call open source. So what open source means is that these guys on the right-hand side designed this piece of equipment, but they gave away all the plans for it. So you could go and build one of these right now if you felt like it. You could get the resistors and the capacitors, the types of headers you have to have on there, and you could build your own. You could call it the Teach Arduino and sell it commercially. They've given all this away. The whole purpose behind this was to give artists and teachers and engineers a platform that they could work with where they don't have to do the soldering together every single time they want to do a project. This is already built for you. And since it's been around for so long, it's been about 10, 11 years that this platform has been around. That means that there are hundreds and thousands of resources to use with these. So it's, once again, I just want to give you the big idea of everything there. Don't get too intimidated by all of the different stuff and the different choices. We'll get to that in a little bit. As far as Arduinos go, there are these 5 official Arduinos. They come from the official company. If you start reading in the news right now, they're having a little bit of a rift that's going on, but we still work with the genuine Arduinos, so that's why I'm showing you here. The Arduino Uno in the upper left-hand corner, that's a great beginner board, and it's what we send out with our Space Kit, and it's what's powering the demo sat at the moment. And you can see these other ones. They've built ones that are smaller. They have ones that are bigger, that are like for 3D printers or big robots. If you've seen those competitions on TV where there's a big robot throws a basketball into a hoop, there's a good chance there's an Arduino Mega behind that, which I don't have pictured right now. There's another one that they're just little tiny ones that are meant to be sewn into clothes so that when you're wearing a shirt and you go outside and it gets UV rays, something changes on the shirt. But there's all sorts of these. Like I said, since they're open source hardware, people's imagination can run wild and build all sorts of particular use case Arduinos. The one that I just showed in the corner here, that is the one that is going to start coming with our Space Kit. It makes everything easier. So like I said before, when you work with an Arduino, you're getting all of the electronics hooked up together, and you can just plug in things into it. So you can plug in sensors, and you can plug in lights. You can plug in inputs, things that are sensors and take in input, and then output like lights, or you can have a computer do something or a motor work. Input output is the basis of everything you're going to do with an Arduino. It's just work and training and imagination and innovation after that. So the reason we're moving over to this other board is you'll notice in some of the other boards there's these connectors, and a lot of times we have to have single wires to hook up to sensors. This one in the corner, someone put a different connector on there, so it's just one wire with 4 connectors that hook up sensors. What I like to tell people about this when they say, how long is it going to take? It has already been so simplified that if you would look at 12 years ago, before this existed, you would have had to learn soldering, electronics, PCB boards, all that sort of stuff. On top of, you would have had to learn your own code because there wasn't a unified one that was going to work on any of these things. So we keep taking off the more and more stuff off of the front end of learning this. So you're coming in at a good spot. This is a great jumping on point for this sort of technology. So why is it a good learning platform? Like I mentioned, with those not having to solder and whatnot, you can do rapid prototyping. So in the engineering design process, excuse me, in the engineering design process, what you're trying to figure out is a solution to a problem. And good solutions to problems have many, many iterations. Have an example for this, like art classes that make pottery. If a class they did this study where half of the class was supposed to make a pot and they could only work on it one time, and the other half of the class got to make as many pots as they wanted, and their last one could be the one they could turn in. And always, the pots always turned out nicer from the people who did it a whole bunch and learned from the last time that they did it and failed, probably, rather than the person who worked on just one and just worked on that one and didn't learn anything from iteration. So that's why this is an amazing platform. Instead of doing all that soldering back and forth, you can easily pull out a sensor and say, hey, this one's not working for my solution. I'm just going to plug another one in. And when you see students and teachers, when they're working with this, just seeing their minds expand into, oh, if I can get a light to blink, the world's open up to me. So that's why it's a great learning platform. I mentioned the big scary code. I hope I'm not losing anybody by mentioning code. Just breathe deep. Code is not scary, especially with an Arduino. What's awesome about Arduino is, like I said, since it's been out for 10 years, it is not the fact, learning the code is fine, and if it's something you want to do, go for it. I've been working with Arduinos for about 10 years, and I think off the top of my head, I could give you 2 or 3 things code elements that I could just type out from off the top of my head. Everything else I do with an Arduino is I go and find somebody who's already solved this problem, get their code, which vast majority of people just give away for free. You can grab their code and then you can plug it into your project. And then, so the more important thing comes, where do I find code and how do I integrate it into my project? Which is what takes me to the next slide here. Finding code, there are a lot of great communities online that the point of them is to share code and share ideas on projects to do with the Arduino. So you can see upper left-hand corner, you have the official Arduino boards. Thousands of people that have been on there for years answering all sorts of questions. It's a good chance that your first question will be able to be answered there. Upper right, you can see Instructables. This is an amazingly cool website, and it has an Arduino section. So it runs the spectrum, since it's user-generated content, it runs the spectrum from textbook quality information, instructions, to very vague, blurry pictures, and not 100% sure that it works. But there's lots and lots of code in there. Like I said, the skill is more on to finding the code on these resources. SparkFun. It's one of our vendors. They provide hundreds of different sensors, and for those sensors, they provide code. So code that makes a temperature sensor work, or code that makes a inertial measurement unit work that's available on their website. And then I humbly present ardusat.com/license. And you have we hand out all of our code right now as open source, so you can run with it and enhance it, do it exactly the way that we have on there with the instructions. Feel free. So now you've got 4 amazing resources to find your code that's most likely going to have the stuff that you want. You're welcome. So talking about sensors. Sensors, the input. This is a really fun part of working with Arduinos. What you're seeing here on the screen is in the upper middle, that's a infrared thermometer. You can point it at stuff and it'll give you the surface temperature of that object. The one in the upper right is a muscle sensor. The one in the lower left is a inertial measurement unit. So you can put that into something you can check how fast it's going, the acceleration, or how many g-forces it's pulling. If you wanted to try to measure it, it's a good chance there's a sensor for that out there. So if you want to figure out, like if you wanted to have kids in your classroom measure their heart rate or their temperature or some other health science thing, if you want them to see who can take a yo-yo and spin it the fastest, all of that stuff is available on this. So just know that, once again, it's the combination of some of these things. So where you come into it is finding the code, finding whatever sensors or outputs need to work to solve the problem you're trying to solve, and then putting those all together. There's a lot of places that have sensors available. You can see SparkFun, Adafruit Seed, and I've got a place on our website that has all of these links to all of these places. So don't worry that I don't have it up right now. We'll get that information to you in an email after we're done with this presentation, but it's available on the website. eBay is a great place to look. There's lots of vendors that are straight from China that will send sensors that end up being very inexpensive, but very powerful to work. Like you can see, there's one on there that's 91 cents. That's an ultrasonic. It tells how far something is away from each other, so it's a lot of basis on robots. It can see whether it's getting closer to a wall or to an object, and then you can tell it, hey, make the Arduino say, when you get too close, make the motors go backwards and turn so that you can get out of the way of the object. Once again, I humbly present the ArduSat. The ArduSat Launch Pack and the Space Kit. Basically, we've already curated what we think is the best set of sensors to learn about Arduinos in space and STEM projects, and we put it all in a kit for you. So it's super easy to just buy that, and you've got a great starting point for all the Arduino projects that you want to run. So we've talked about input, that's sensors. Now let's talk about output. One way of getting output from these sensors is through data visualization. So in the upper left-hand corner, you can see a window that says COM9. That is the serial window from the Arduino IDE, the software that you use to get programs onto an Arduino. You can see I've taken acceleration data, so I'm using an IMU sensor, and you can see that it has numbers that are going down. So if you move the sensor around, those numbers change. If you have a temperature sensor, then the temperature would change and it would show you those numbers. Well, seeing the numbers is interesting, and if it's just one number like a temperature, it's pretty easy to see through that. But if you've got something like acceleration where you have to plug in a formula to actually use the 3 pieces of data to get your g-forces out of it, you can see up at the top what I've done with those numbers. I've put them in Excel, and then I put them through like I said, a formula, and then made a graph at how that formula works. So you can see the one that says bubble wrap data set. That was when we actually took one of those acceleration sensors and threw it off of a balcony with bubble wrap around it. And you can watch that video and a lot of those results actually off of our website and in the community, which I'm going to be giving you the address to when we're done here. But you can see how much more interesting it is when you have a graph. You can actually see how long it was falling, when it hit, how hard it hit, how many g-forces, and then start thinking about it like, what if you did that with a whole bunch of different packing materials. So you try popcorn, bubble wrap, you try a parachute, fly it with a drone, something to that effect. Then your students can start comparing those results. What we've designed some of this for is to make an egg drop. You remember the egg drop experiment that people do in school? You put an egg into a container, throw it off of a high place, and see whose is protected and whose egg breaks. What sensors in an Arduino does is it adds data to that drop, so you can find out how long it fell, what the g-forces were, and then you can add a little bit more science rather than a whole lot of luck as to why someone's egg broke and someone else's didn't. We've found, we think that this is so important to have off of the input of the sensors that we've built what's called the experiment platform. And so you can plug an Arduino straight into this experiment platform, and it will do all this data visualization for you for all of the sensors that come in the Space Kit and that are on the demo set. So the launch of that's going to be really soon. So make sure that you sign up for our newsletter so that you get the latest and greatest for seeing when all of these, when all our new products are going live. So what could you do in the classroom with a set of students? I've seen a classroom create an incubator. This is an automatic incubator. They have a set of eggs so that it stays warm enough for the eggs to hatch. Has a relay, temperature sensor, LCD, a battery, a fan, so that instead of someone just having to remember to go turn off the light at the end of the day and turn it on, it does this all automatically. Great class project. And I have a link to this project so that you can see step by step exactly how to do this and what materials you would need. Same with the Jackolantern here. This is a really cool project. Halloween's coming up real soon, so this is topical. What they did is they took a craft store Jackolantern and cut some eyes and mouth into it, put LEDs into there, and the LEDs flash, but if you push the button nose, the LEDs stop, and then they come on again really bright, and a air horn blares from the inside of the Jackolantern. So it's a really good scare. So once again, Arduino powering this, and a link to that whole project if you wanted to do that one. Our favorite project that we have on the website right now, we call the zombie detector. What this is it's two sensors. It's a light sensor and a temperature sensor. And what we said was the problem that this circuit was fixing is we have a hypothesis that says if someone was a zombie, they wouldn't have blood in their system, so their skin would be colder than regular humans. So we built this circuit so that what you could do is you could put your hand over the circuit and it would flash green if it thinks you're human. It detects normal human temperature, or it'll flash red, signaling a warning that, hey, this person might be a zombie. So the way that we have teachers use this in the classroom is it's kind of a game. We get cold cans of soda or something to that effect, and we get like 3 warm ones and 1 cold one. And then you give, not cold one like that, it's a cold can. So take it easy, it's a school. So, but if the kids hold on to the cans, and the one who's holding the cold can, they hide it from each other, and then they try to figure out who's the zombie, and then at the end of the game, everybody puts their hand over the sensor, and then the person who's been holding the cold can of soda it will show up as a red light, and whoever guessed that was the zombie gets a point. My son, who's 9 years old, so if you're wondering like what the age ranges are on this, he was 9 years old at the time. He used this project as his science fair project, and it worked out amazingly well. Once again, I wrote an article on this on our community that you can go check out, see some pictures of what they did. But what happened was that basically the whole class gathered around his project for most of the hour, and even teachers and kids from other classrooms wanted to see what the commotion was and came over to see it. And for entertainment value, it was super, super great. But what was awesome is he was interested in the project enough that he learned about IR radiation and was able to explain it at a 9-year-old level, explain how this was detecting the heat off of his hand. So great success there, getting him interested. He talks about wanting to build this circuit again over and over. So we figure it's a really good success. We have a local school here called AISU that is a alternative charter school that works in week-long intensives. So the students work on one subject for about a week. And so we were honored to go and help them out with one of their week-long intensives. At the beginning of the week, they did our getting started guide so that they could have a foundational knowledge of how to work with an Arduino and with electronics. But throughout the week, they were asked to solve their own problems, like whatever you want to build with the Arduino and the sensors and some buttons and wires, you could build what you wanted to build. And I was just amazed at how many different and creative, innovative things that the kids came up with. You can see they came up with like a robot. They came up with several games that, if they worked on them a little bit more and refined them, could easily become viable commercial products. And they even built some musical instruments. So, but they were all learning the same thing, but they were working together. It was amazing to see the ingenuity and the creativeness and the interest. Nobody actually fell off on Thursday and was like, well, Arduinos, I'm done. Everybody wanted to work on their project until the last minute, and some of them just had to be told, look, you're delivering your product, you can be done now. So I've done a lot of talking about Arduino, the backstory, projects in your classroom. So what's some practical advice when you start introducing Arduinos into your classroom? We recommend that you have a ratio of 2 to 3 students per Arduino board or per Arduino kit. Unless what you're trying to do is have every single kid have their own experience on it, that's fine. But we find that the collaboration, like I was talking about in the AISU example, is where a lot of the magic happens. There's a chance for someone to do a little bit more code. There's a chance for someone to do a little bit more building and research. And so when the students are coming up with ideas, it seems that they come to better solutions by asking each other questions, by saying, how do you think this should work? Should we try a different sensor? Maybe if we put the lights in backwards, that would work. Try to figure it out. And that process of troubleshooting and iterative solutions comes to a better project than I think that, depending on what you're trying to get to, but then one student would do, or 4. At 4 or 5, then there's going to be a student that's going to be left out that could just slide by adrift through the project, and we don't recommend that. So label everything. There's so many little bits and pieces that come with these different sets that it can get easily confusing. And some of the sensors look like each other. Since some of them come from the same manufacturer, they look similar, and they're just a little bit different in size. So you want to make sure that they're clearly labeled so that the kids can put them together into sets and know where each one is. And it's I'll move on to the next one here since I'm talking about boxes. We recommend clear containers for everything. Big clear containers, small clear containers, because there's nothing more frustrating than going to I guess there's lots of things more frustrating, but when we're talking about this context, going to an electronics thing and having drawers that you can't see inside and opening and closing every single one, trying to find where did we put the temperature sensors this week. And so there's 2 ways to go with organizing these. One way is to have the kit and then make sure that the kit always has all of the stuff in it. So it has one IMU, one temperature sensor, all of the wires it needs, and then you can put it away and then have the kids, if it's checked out to them, they can be responsible for their own kit. The other way, and this is the way, if I'm personally running something like this is the way I personally do it, is that I will take all of the kits and I will separate each component out and put it in its own container. So you can see here on the picture where it says temperature, luminosity, UV. This is what I would actually do in a classroom so that the students can go to the station. They're cognizant of which components they actually need. There's no chance of breaking a component that is not involved in the project at that point. And it's a lot easier to keep inventory, because what the students can do when they come back is they put them all in the correct place. And then you can have 1 or 2 people that are in the classroom that are the inventory people. So when everything's put back, they count out how many luminosity sensors, how many UV sensors, and I think it works. It all depends on if you're sharing these around classrooms and you need to move it, then you can go with keeping the kit together. But I just wanted to put those 2 ideas out there to get you thinking. Maybe you'll come up with an even better organization idea for this, and when you do, you go ahead and let me know, and I'll let everybody else know. The less us, more them. This is more of a philosophy than like where you should put things in your room. But less us, more them means that we as educators get the students enough information to get started so that they're not just stuck at the very beginning without any idea what to do. But then letting them go, taking away things that they already know how to do. So at the very beginning, doing a getting started guide and then going through all the steps, and then their first project, making it a simple one so that they know how to hook things together and get code together and whatnot. But then on the next project, don't tell them which sensor they're going to use, or don't give them the code and say they've got to go out and find it. So it's this scaffolding process where you're giving them the baseline and then taking away a little bit at a time until you get all the way, like the way that we're going to do this is we're going to be taking away a little bit of things, a little bit of instructions until all the way people get into space and they have to come up with everything. They come up with the question, we'll help, we're there, you know what I mean? But by then, people should be really good at coming up with a question, how to work with the sensors, and how to communicate back and forth. So I fall into this trap sometimes. I still adjunct at a local liberal arts college, and I feel sometimes like I need to tell the students everything or else they're going to miss out on something. But like the AISU students had, giving them the creative freedom to try to figure out a lot of their own problems and solutions, I think ends up being a lot more of a productive and good learning experience. Here's a small lit review that I came up with. If you want to grab some books, if you're the type of person that loves to read a book to get the foundational knowledge of what you need to move on, I recommend these 4 books. Invent to Learn is great. Once again, it's more of a philosophy book about actually working with all sorts of different electronics and maker movement type things in your classroom. You have the official Make Getting Started with Arduino, which was written by Massimo Banzi, who is one of the people who invented the Arduino, so straight from the horse's mouth there. Makers, The New Industrial Revolution by Chris Anderson. Once again, this is a sort of a philosophy thing, but it is telling us exactly how the Industrial Revolution is, or the maker revolution that we're having right now is exactly like the Industrial Revolution. We are getting these products that are so cheap, so easy to use, that people are creating just these amazing things out of them. And that's what people are going to do in jobs going forward. They need to be the people who are taking existing stuff and combining it and making new products. So if you want to get into the why this is important so students can be ready for the jobs of the future, this is a great book to start with. And then Arduino Workshop is just great. It has a whole bunch of simple, it goes from simple to very complex projects, and it builds on each other. And so if you need a book that you'd like with more projects instead of looking at a website, that's a good one. And so, Chris, this is great. Wonderful. Now, me as a person who wants to learn Arduino, what should I do? So, big picture of this process, get some Arduinos. If you already have some, great. If you don't, pick one. And come to us for some recommendations. Once again, I'll humbly recommend ours. But if you were going to go out and get an Arduino Uno, or if you were going to get a clone because it's cheaper, that's just fine as well. You know, vast majority of these just work out of the box and they're just fine. So get some Arduinos and get some components together. Then do a getting started guide. Come and do ours, do the official one, some sort of getting started guide, because that will get you down to what you need to start. It'll help you get an LED to blink from your code. It'll help you get maybe test your reflexes by putting wires together, give you all the basics of what you need to know, and it gets you over that hump of I don't know what I'm doing. Then once you're comfortable with that, add a sensor. Find something that you want to measure, and find the cheapest sensor. Just find one that you can work with so you can see how input and output works. As a matter of fact, a button counts as a sensor. If you just have a button that you press to put 2 wires together, that counts as a sensor. You're giving something an input, and the Arduino is giving an output, which is, like I said before, it's the basis of everything. And then plot some data. Look at the data and then try to see how you'll have this moment where it's really cool to see the data visualized and say, oh, this is what I'm working with, and I can compare it easily now. I'm a huge fan of project-based learning, worked with it for years at the college I used to work at. So I would say come up with a project to build. Come up with something. Figure out if you want to make your coffee mug tweet every time that your coffee's ready or it's a certain temperature. Some other ideas. Find out if, using a magnetometer, find out if using one magnet, how strong one magnet is, and then if you have a second magnet of that same size, how much more powerful does the magnet become? Does it come exactly twice as powerful, or is there some sort of fraction that you could use to say how much stronger it's getting? You could put a temperature sensor into a hot car. Park your car in the morning when you go into work, put your temperature sensor in and let it read the data all day, and figure out how long it would take for the temperature inside of your car to become dangerous for a pet or a child who was left in the car. I think you'd be surprised how quickly it happens. Or vampire electronics. Anything that's plugged into the wall is drawing just a little bit of power. So even if you turn your computer off or your TV off, there's still just a little bit of power that's being drained. And so there are sensors that you can get that you can clip around a power line, and it'll tell you exactly how much electricity you're using. And you could find the biggest vampire in your school or in your house, and then see if there's something you can do about it. Either turn it off at night or replace it with a more energy efficient machine. So I've talked a lot, and I hope all of that made sense. Okay, we'll go ahead and wrap up from here. We can continue this conversation at community.rdusat.com. Once again, thank you guys for participating, and have a great evening and afternoon.